So yesterday you looked at some Desmos concepts and you were looking at specifically what happened to the graph when we applied certain transformations. So I want to just kind of review that, and then we're going to go over some examples to kind of show you how these look in real problems. So the first one is translations. This is a shift. Okay, and there's two different types of shifts that happen. The first one are horizontal shifts. And those happen when we add or subtract inside the function. And again, I'll show how that actually looks with a real function in a second. We also can see a vertical shift. And that happens when we add or subtract outside the function. Okay. You'll notice that we had a horizontal reflection. When we make the inside of the function negative, we have a vertical reflection when we make the outside of the function negative. All right, and then for dilations, really what I want you to do is I want you to just focus on the fact that if you are multiplying by anything, that means that there's a dilation. Later we'll get into really, is it stretching vertically, is it stretch, or is it compressing vertically versus horizontally? Those all kind of get a little confusing. So my suggestion is anytime that there's a dilation, for now, let's also make a table to help you out. So anytime that you're seeing the multiplication of a number either to the inside or the outside of the function, we're going to make a table to help us. Okay, so here's our first example. If I have y equals the absolute value of x plus 2, I want to be really clear. You can always make a table of values. You could plug in whatever values you think appropriate. So like -3, -2, -1, 0, 1, 2, and you could always make that table of values. However, I want to show you an alternate method that can be more efficient and can really help you to kind of recognize what the graph is going to look like before you actually graph it. So what I want you to do here is, first thing, think about the parent function. In this case, it would be y equals the absolute value of x. So a reminder, the parent function here is the absolute value graph, which means that my general shape of my graph is going to be that V shape. Okay. The first thing that I want you to do is I want you to actually graph that parent function. So we would have a point on 0, 0, and then a point on 1, 1, 1, 2, and so on. Okay, and I'm going to try and do my best with this. Again, I apologize because my computer won't let me do straight edges. So this is the graph of y equals the absolute value of x. Okay, now we don't want that though as our graph. We actually want y equals x plus, or the absolute value of x plus 2. So what we have to think about is, okay, using our knowledge from what we did yesterday, what would be the transformation on this? So because I'm adding to the inside, this would be a horizontal shift. Now, if you go back and you look at your Desmos activity from yesterday, the thing that happens with the horizontal shifts, though, is that we actually go in the opposite direction of what you think you should. So in this case, this is plus 2. We're actually going to shift to the left 2 units. And so what I can do is I can take all of these points that are on my graph and I can shift over 1, 2 units, over 1, 2 units, over 1, 2 units, and I'm moving all of my points on my graph 2 units to the left. Okay, and I'm going to go ahead and try and sketch this as best as I can. All right, not perfect, but we'll go with it. So this would be the graph of y equals the absolute value of x plus 2. Okay. Now, when you actually graph these, if you're going to graph in this method, what I always want is I want you for you to have the last or the only thing there to be the answer to the question. So we should erase everything else that's there. Okay. Now we should always add arrows on the ends, and we should give some values. So 2, 4, 6, 8, 10. And this would be -10, -10, +10. Again, I apologize. Yours should look a little bit straighter than that and a little bit more accurate, just because I want you using a straight edge on anything that should be a straight line. Okay, so my answer here would be this graph. Notice that I did this without using any type of table of values. I answered these questions up above. What is the parent function? The parent function was y equals the absolute value of x. And any transformations, that was that horizontal shift. On the next example, I'm going to actually show you a little bit more of a shortcut method so that you're not having to draw out everything, okay? All right, here we go. So we've got y equals the absolute value of x minus 2. So again, what is the parent function? Well, the parent function, again, would be that absolute value graph. So the general shape of my graph is going to be that V shape. Okay, now what we want to look at is we would say, okay, well, here's my parent function. Rather than graphing the whole parent function, I'm just going to plot a few points because this will kind of help me. I usually do 5 to 7 points. Now what we want to do is we want to identify what's the transformations. Well, notice that I'm subtracting 2 from the outside of the functions, outside of the absolute value. So what I would have is I would have a vertical shift down 2 units. Okay, a vertical shift down 2 units. So notice that I didn't graph the whole graph, but I still have these points here. So I'm going to still do the same idea and take those points and move them down 2 units. So shift down 2 units, down 2 units, down 2 units, and so on. And now it's just so much easier to just quickly erase those points, and we can connect the points on the graph that I drew. So this graph is the graph of y equals absolute value of x minus 2. Again, give ourselves some labels. Okay. All right. For this one, we are going to be looking at a dilation. So this would be, notice that I'm multiplying by something, okay? So first, let's again start thinking about the parent function. So what's the parent function here? Well, the parent function is whatever is kind of that primary piece of the function family. So this would have y equals x squared in it. So a quick reminder, we'd be looking at a parabola, okay, or that U shape. And now, since we're multiplying by 2, and we're multiplying to the outside, we're technically going to call this a dilation, or you could also call it a vertical stretch by a factor of 2. Okay, now if you were to just call this a stretch by a factor of 2, I'm okay with that. If you were to call it a dilation by a factor of 2, I'm okay with that as well. The main thing that we need to know, and I'm going to show this to you actually in a table of values as well, is that what this means is notice how if our parent function has y is equal to x squared, notice how all that I'm doing is I'm multiplying that y value by 2. So we will multiply each y value by the factor, in this case 2. Okay, so coming over here, if I start with my parent function, I'd have the point 0, 0, and this, all of these parent functions you should know. So then when I plug in 1 for my parent function, I get out 1. Same thing with -1. When I plug in 2, well, 2 squared would be 4. Okay, I plug in 3, 3 squared would be 9. So when I go to apply this vertical stretch, all that I have to do is multiply each y value by a factor of 2. So I'd start here at 0, 0. Here, when I'm at 1, 1, well, the y value is going to multiply by 2, so it's going to become 1, 2. Same thing with -1, 2. And then I would have over 2 up. Instead of 4, I'm going to go up 8. Instead of 2, I'm going to go up 8. And then I can erase the other points and graph. Now, if that whole multiplying by a factor of 2 doesn't really work for you, keep in mind, especially on these ones where you have a dilation happening, it is perfectly acceptable to go ahead and make a table of values. So if I were to plug in -2, -1, 0, 1, and 2, I would have, when x is -2, I'd have 2 times 4, which would give me 8. When x is -1, I would have 2 times 1, which is 2. When x is 0, I would have 2 times 0, which is 0. When x is 1, I'd have 2 times 1, which is 2. And then when x is 2, I'd have 2 times 4, which is 8. So notice I get the exact same points. All right, so now this one's a little bit different. Because I have the multiplication of 2 on the inside of this function, a way that I want you to think about this is I want you to actually think about this as 4x squared. Okay, notice if I were to square everything, I would have 4x squared. My parent function is still going to be y equals x squared. So we're still going to have that general shape of the parabola. And then I would be multiplying by a factor of 4. So this would be a vertical stretch by a factor of 4. Okay. Another way that you could describe this is you could describe this as a horizontal compression. And when I get back, that's easier for me to show you in person why a vertical stretch is the same thing as a horizontal compression. So I will show that to you just visually when I get back. But for now, we'll just go ahead and call this a stretch by a factor of 4. If you were to call this a dilation by a factor of 2, I'm okay with that as well, because it technically is a dilation by a factor of 2. But I want to give you more of a visual as to why it's horizontal in that case and not vertical. So going ahead and graphing this, I'm going to graph this without the table, just using what we had practiced as far as multiplying by the factor. So if I start here, I have these as my points. Okay, and then I'm going to multiply all of my y values by 4. So I'd have 0, 0. 1 is going to go up to 4. And then when I'm over at 2, I would have, ooh, well, that gets really high really fast, doesn't it? When I'm at 2, I'm normally at 4, so that means that I'd go up to 16. So when I graph this, I'm going to come down from the very tops. Ooh, it is really hard to graph with this pen. So do your best to make that rounded at the bottom, because at the vertex there, because this actually is a parabola, so we don't want it to be too V-shaped. Okay. There you go. Okay, so for this next one, notice we're still dealing with that y equals x squared, so it's still going to be a parabola shape. This time our transformation is dealing with that negative. So the negative is on the outside of the function, I'm multiplying negative and then I have the x squared, as opposed to the negative being on the inside of the function, so inside of the squared. So for this one, I would have a vertical reflection. And a vertical reflection means that you're taking your graph and you are going to reflect it vertically. Okay, that would be a vertical reflection. It's not a reflection across the vertical axis, but instead we are flipping our graph down or flipping our graph up, depending on the portion of the graph and what type of parent function we're using. So again, start with your parent function. I always like to draw in these points. I think it's helpful and it allows you to not make as many mistakes, and it really gets you to know those parent functions really well. And then we're going to take all of those points and we're going to just reflect them across this x-axis. So 0 would still stay there. At 1, 1, now I'm going to move down to 1, negative 1. Negative 1, 1, I'd be at negative 1, negative 1. And then over at 2, 4, I'm going to move down to 2, negative 4. Okay, and there would be 1 down here too. I'm realizing that I may have forgotten to put some labels on my last graphs, so I apologize for that. Let's give these some labels while I'm thinking about it. Negative 10, and 10. And then we'll go back and erase those points. Those points didn't take us long to do or long to erase, and it's really helpful. And notice we just graphed that in like maybe 30 seconds. And we didn't have to make a table of values. We didn't even really have to think about it all that much, other than the fact that there was this vertical reflection. Okay. All right, so let's go ahead and bring all of these together. What happens if we have more than one transformation happening at once? I apologize, I couldn't think of what the word was. So first you'll start with your parent function. So in this case, notice I have absolute value. So at its core, this is going to be an absolute value graph. It's going to be a V shape. Okay. So if I start with my parent function, I'm just going to graph those points. Okay. And now what we want to do is we want to list all of our different transformations, and we want to do this in a specific order. So the first thing that you want to deal with is you want to deal with any stretches. Okay, then the next thing that you want to deal with is you want to deal with any reflections. And then the last thing, it should always be your last thing, is any shifts. Okay, I'm going to color coordinate this, but then again, we're always just going to plot the points and then we're going to kind of erase as we go. So the first piece is, are there any stretches? Well, is there any multiplication happening here? Yes, I'm multiplying by 2. So I would have a vertical stretch by a factor of 2. Okay, so all of these points, I'm going to multiply by the y value by 2. So when y is 1, it becomes 2. When y is 2, it becomes 4. And when y is 3, it becomes 6. Okay, notice that what happened to my graph here is that it just got skinnier. That's why it's a vertical stretch, is that it looks like it's getting taller and skinnier. Okay, so I'm going to erase as I go. Get rid of my parent function now because this is my newest function. Okay, now the next piece that I want to deal with is a reflection. So notice that I do have that negative on the outside. So I'm going to reflect vertically. So this is a vertical reflection. So I'm going to move all of my points down across that x-axis. And I'll go back and I'll erase the red ones because those are no longer relevant. All right, then the last piece is any shifts. So I see 2 shifts happening. It's important that we focus on both of them. So we're going to shift vertically. And because we have -1, we're going to go down 1. And then we're also going to shift horizontally. And because we're adding 2, that means that we'd go to the left 2. Remember, when we're adding to the inside, we could do the opposite of what we think it should do. So now each of these points, I'm going to take and I'm going to move them down 1 and then over to the left 2 units. Okay? Down 1 to the left 2 units. Down 1 to the left 2 units. Down 1 to the left 2 units. Down 1 to the left 2. Down 1 to the left 2. Down 1 to the left 2. Okay, I'll go back and I'll erase those green ones just so that they don't confuse me. I'm going to erase the other markings that I have as well. And then we will graph. Done. Now, could I have made a table of values? Absolutely. Did I need to? Probably not. And I think that as you get more and more familiar with this, you'll get more and more comfortable with it. So on your homework, I'd like for you to try graphing using this method. I know right now it might seem like it takes a little bit longer and you have to think a little bit more. If you really get stuck, make a table of values, but I really want you to try to think about the graphs in this way because it will really help in the long run for you to understand that. All right, so here's our homework. 15, 18, 22, 24, 26, 28, 33, and 36 on page 114. Your job for the rest of the class period is to be working on this. So give it a shot, see how it goes, and then I will be back on Monday. So tomorrow you're going to have a review day, and then on Monday I will be back for a second review day where we can talk some more. Have a great weekend and have a great day.